Hello everyone, welcome back to this course. And we have been dealing with the steps of data analytics. And last lecture we have seen different steps are involved in the data analysis stage. And in data analysis itself, we have various ways to analyze the data or various ways to model the whole data. We know that acquiring data, and we did pre-processing, and after pre-processing we do the actual data analysis process, and then finally we go for the results and insight from the data. So these are the various steps involved in big data analytics, and among them this data analysis part is one of the prime part. And in this data analysis we have various sections like regression, classification, clustering, graph analytics are some of the ways we can analyze the data. So today we are going to focus on the regression. So let's see what regression is. Basically regression has different types, like a linear regression, the logistic regression. So before we go on to the definition, let me just classify the different types of regression. So we have the simple linear regression and multiple linear regressions. So as the word suggests, they have some linear relationship between the variables. And comes the logistic regression. They again have this simple logistic regression, multiple logistic regressions. So we are going to focus on the linear regression part, and we'll see some examples on how to handle these regression and how these linear regression help us to predict certain data. So basically this is the definition of linear regression with regards to statistics. A linear regression is a linear approach for modeling relationship between a scalar dependent variable y and one or more explanatory variables or independent variable x. So at times when you have only one explanatory or independent variables, we call it as simple linear regression. When you have more than one of the independent variable, we call it as multiple linear regression. So that's the basic definition. So we are going to establish this relationship between these two variables. So that's a core idea, and as you can see from these two variables, we can try to predict values based on the data that we have. So here is the basic linear regression equation that we have in hand. So this is the first order linear model equations. It's a simple linear regression model where y equals beta naught beta 1 x plus the error factor, where beta naught is the y-intercept, as you can see here. Beta naught is the y-intercept, and beta 1 is the slope of the line. So we will come to this part soon. Beta 1 is the slope of the line, and x is the independent variable, y is the dependent variable. Let's consider, for example, here if you want to have a value of x, say for example you have a value of x here, and you can correspondingly you can look at its value for y as well. So what we are looking at here is the slope. Let me do it again. So beta 1 it is the slope of the line, and it is also can be referred as the coefficient. So we can calculate this coefficient. It's the coefficient. Suppose you have a value in x here, and then you ought to predict the value of corresponding value there. So you can project it to this linear line that we have. This is the regression line that we have there, and based on that you can actually see the actual slope over there. For example, if you want to look at this section here. So you have the difference, say for example x1 and x2 is here. So between x1 and x2 there is the difference that happens in the slope. As you can see that the variation of y is clearly evident during that space. So with this values, let's say this as xi and yi, with these values we can actually predict or find the coefficient that is beta 1. So we will go to see how this can be used in analyzing or predicting data in the coming slides. So here is an example of house price prediction. So there are values given to us in terms of square feet and price, and let's see how these are distributed. So this is a simple scattered plot here, and suppose I want to say, let's want to buy a house, and let's say our house requirement is like certain square feet. For example, we are looking for the house in this particular range of square feet. But as you can see there is no particular data is available at that particular range. Or maybe we can say, okay, this is, say, let's say this is like 2000 square feet example, and at this 2000 square feet there is no house available, so we don't know exactly the price of the house. Maybe then you can look for another range, say, let's say we are going to take this range, and in this range we are trying to see what is the price that we are going to have. But again, we have only two houses that are displayed in our data, and from these two houses it's very hard for us to predict the actual house. Even if you look at the other side, still you have only like two houses. So overall range, the whole range, say let's say it's like 1500 square feet to 2500 square feet. So among this whole range you just have four houses, so it's very hard to determine the exact price. So we can model actually a simple linear regression way to predict the housing price. So here is the equation that we talk about. And if you recall, the equation of a slope also resembles the same. So here's y equals beta naught plus beta 1x plus the error. So we are trying this linear line, and you can see it also has the intercept on the y-axis. So let's consider having several lines, and let's see which is the best fit line that is at hand. So that's very important. We have to find which is the best fit among all the lines that we draw. So initially I have just drawn one line, and that covers most of the region, and we have to see which is the best fit line. And how do we find this best fit? So in order to find the best fit line, what we do is that we do a ordinary least square models. So in this method we measure the unknown parameter in the linear regression. For example, the main objective here is to minimize the difference between the observed data and the predicted response by linear approximation. How is this done? So for example, like we have several lines drawn, and we have to calculate the actual sum of squares of error of each and every line, and then finally we can make a conclusion that whichever line has the minimum sum, that is the best fit that you have in hand. So let's see how to do that slowly, one by one. Let's look at. So okay, here is only two of the line is given just for our reference, and we can try to fill in the information here, x, y, and let's suppose I want to find the sum of errors. So we want to find the actual part here. Let's say I will observe, let's say, sum of residuals. We are going to have the sum of residuals, that summation I equals 0 to k yi minus yi dash the whole square. So we are going to have these two values, yi and yi prompt. So let's say you have this value here, and let's try to see its distance. Okay, so what we are going to have is, this is going to be your let me just give it a try here. Let's say this is the line, and you have this point here, and you are projecting it over this part. Let's say this is the yi and yi prompt. So you are going to form yi minus yi prompt plus y2 minus y2 prompt. So since it's of I, we are going from 1 onwards till all the values are covered. And so on. So as you go across this whole thing, you can see that this, if you project it over to the y-axis, what you get is the observed value of x for y. So that is your actually observed value, and the predicted value is actually over here. This is the predicted value. Say for example, if we are talking about the experience, and if this is the salary, and let's suppose that this is 1, 2, 3, 4, 5, 6, and so on. So number of years of experience, and say for example this particular point is, say, let's say it's 3 years. So with 3 years of experience, and suppose we'll have some values here as well, say 20k, 30k, 40k, 50k, 60k, and so on. Okay, so also look at this equation here, beta naught plus beta 1x. This is our equation that we have for the linear model there. Okay, what is y when x is 0? In other words, with 0 experience, what is the value of y? The value of y is going to be beta naught, and beta naught here is our beta naught, which is 20k. So with 0 experience, you can earn 20k per year. I mean 20k US dollar if you consider it is in US dollar. Well then, now we are going to look at for 3 years of experience, what's going to be my salary. So with 3 years of experience, as we project to this linear line, we come to know that our predicted value is only 40K. So our predicted salary for 3 years of experience is 40K, but according to the data, we have observed that the value here is almost 60K. So that's the difference that you have between the predicted value as well as the observed value. So in the same way, you can see at various stages you have both predicted value as well as the observed value. So this green line indicates one of the linear regression line, and there is another line, gray line. So we can actually also do the sum of residuals for that gray line with the same equation, with the same method, and we can compare this error. We can compare this particular residual error, and if the residual error of gray is smaller than the sum of residual error of the green, then we could say that gray line best fits the equation. In other words, that is the best line that we have. The same is true with the green. If green is the smallest, then we would go for green. So we will consider more about this information. Let's suppose you have let's consider the same example, experience and salary. And you know that sum of residue is that summation I equals 0 to k. You have yi minus yi prom the whole square, and we do the whole square because at times you do get negative value. In order to avoid those negative values, we square it so that we get only the positive values over there. And now we are going to introduce another term with regards to this. So we will call that as the R square. So what is this R square all about? So we had the original problem earlier. Let's consider the similar problem and see how this goes on. So let's say you have those datas here. Okay. And with this datas, now we are going to draw a horizontal line, and here we call this as the y average. In other words, it is kind of the average salary. You are drawing the line for the average salary, and now we are trying to see the same thing. Now we are trying to see or trying to compare all observed value with respect to the average value. So these points are all observed values, and you are going to compare that with the average value. So now we will introduce this term. Let's call as y average, the sum of all this information. Let's call it as I equals 0 to, let's say, in terms of 0 to L, and let's say yi minus y average. So here we have this average value. So you can compare this both information, and then you would see how they are related. So now we are comparing with that of the average value. We have both observed value and the average value. So we make the difference between these two and then square it off. So the formula for R square is given by 1 minus sum of residual by y average, the sum of y average. So that's going to be our prime formula for the so-called R square. So now we can see how these are related. Let's move on and see there are a few more terms that are involved in this aspect. For example, we are still now we are talking about a simple linear regression where we had y equals beta naught plus beta 1 x, and what happens when you include more terms? It becomes multiple linear regression. When I say more terms, more independent variables, more terms in x. So what are the possible terms that we can add? So that's where the next topic takes us to the adjusted R square. Say for example, initially we had this y equals beta naught plus beta 1 x. That's a simple linear regression. Now it's possible that you might have a multiple linear regression in which you would have various independent variables. So now we are going to add few more factors to it. So let's say suppose you have from this example that we have here, our y value we had 20 as our y intercept, that is beta naught is 20 when x is 0, our value of y is 20k, and then you have the experience coming in, right? So experience is one of the factor that we had. What else can be added to this? Maybe you can add your skill set. So that can be one of the factor that would affect your salary. So eventually you can also add more information. Say for example, you can also add maybe some certificates that you have got, or even sometimes it also depends upon the salary. But we should be very careful in adding these independent variables because that involves a kind of penalty. So that's where the adjusted R square comes in. So here we have beta 1, beta 2. So anyway, the main objective here again is to sum of residual should be minimum. So adjusted R square can be written as 1 minus R square n minus 1 by n minus p minus 1, where p is number of regressor and n is sample size. So this is very preliminary information that might be useful for us to check it out in terms of adjusted R square. So as we have seen about the residual factor, and we have to consider this because at times when you increase the number of dependent variables, it actually gives instability to our conclusion. So what adjusted R square does is that it actually provides the kind of penalty factor. Whenever you increase the number of independent variables, it tend to provide or tend to give you the penalty. So we should be very careful in adding those factors. Unless or otherwise it really affects the overall output, we don't have to add it. So there are other parts to regression, and as we have seen earlier, I introduced about the logistic regression. So we are not going to deep into this, but simply I want to tell you some points about the logistic regression. Say for example you have this kind of data, and when you have such data, maybe your average value is somewhere here, and how do you fit this kind of data? If I go by traditional way, we are going to use some kind of line, linear regression line, but this doesn't fit all the data, and that's a question, right? Because this is really, even if you take this residual error, it's going to be huge, and when it's huge, we know that actually doesn't provide any benefit. So let's consider if this point is 0 and this point is 0.5 and if this point is 1, and it's more likely that if you want to really combine all these, let's try to combine by means of say a line. Actually it's kind of shifting from 0 to 1. It's kind of two categories you have at this point of time, and at times you can also look at and see that this whole thing is dragging behind, or in other words, initially before this point everything is below average, but after that point everything is above average. So this is kind of a factor that can introduced if you try to draw a different line of regression. We call this as the logistic regression, and it actually provides kind of a classification part. You can actually try to separate two groups, the groups that are related or closer to 0, and there is a group that is closer to 1, and they are again kind of a provides a sigmoid function. As from the structure you can see, it's kind of a sigmoid, it has a sigmoid character. So I am not going to deal more on this logistic regression. We will be considering that in our another course on machine learning and artificial intelligence. So for the time being, I am going to just introduce this regression, and in the next section I will also cover the classification as well as clustering. So that's all for this class, and looking forward to see you next time. Goodbye.